Mm. Okay, let's get started. So, okay, so if I write that this, sum and 1 to 5, you think of it like this, right? I mean, this is just definition, right? So this thing is called this backwards E symbol, if you like. It's like called a summation. So it makes sense to think of this as you add infinitely many terms, right? You just keep adding. Except it doesn't really make sense to add infinitely many stuff. I mean, so we have to like define infinite, right? So we define this, the actual definition. So you could think of as you're summing, but the actual like definition is we're taking a limit of Sn, where Sn is the partial sum. So you sum up to n. And the reason for this is this makes sense now, right? N is a finite number. We know what it means to add finite numbers, right? And then so it's like, think of it as we're adding finite numbers, but then we're doing more and more of that adding. So that's how we define it. So this might look confusing to you all. So because this is just a sequence, right? This is a sequence. So this is like 11.1. It's just a limit of a sequence. So let's see what the sequence is. Yeah. So if I did a clean example, it's this. Right. So this is by definition. Let's use the thing Sn. And in this case, what is Sn? Well, it's sum n equals 1 to capital N, 1 over 4 to the n. It's this sequence. So what is this sequence, right? I mean, obviously, people think of this as S1, S2, S3, S4, all the way to infinity, right? But in this case, we could actually write out what, our S1, S2, S3, S4 are, right? So this sequence is what? If I plug in 1, this is S1, this is sum n equals 1 to 1 of, in this case, an is 1 over 4 to the n. S2 is this. S3 is this. So on and so forth, right? This is S1, S2, S3. Let me just plug it in, right? I'm just plugging in 1 to here, 2 to here, 3 to here, so on and so forth. Okay, so we could write it out. What is sum 1 to 1 of 1 over 4 to the n? Good. And then when I plug in 2, you get the same thing, right? It's 1/4 plus 1 over 16. And when I sum the 3, it's just this, right? Yeah, dot, dot, dot. So you see this all this thing is, all this infinite thing is just the limit of this sequence. And you can see, and now you see why it's just adding, you could think of it as adding infinitely many things, right? Because the limit is just basically what you get when you add it infinitely many times. But this is like a formal definition. Everyone good? Okay. So now that everyone understands, so you could think of this as, again, this is called the partial sum, right? Because it's I mean, it legit is the partial sum, right? I mean, the whole sum is infinite. So here you're only going up to partial part of it, right? You're only going up to n. Yeah, so, okay. So the whole thing is called a series. So we say if this limit exists, so the limit of the partial sum limit exists, we say series converges. If not, series diverges. Yeah. So if you think of this as adding infinitely many things, you start knowing that, you know, in general, like even if you figure out like whether this thing converges, like suppose you figured out it converges, it is hard to know. Oh, this is hard to know what it converges to. Hopefully you all know the difference, right? Converge just means this when you added infinitely many things, you get a number. But actually knowing what that number is another difficulty, right? It's easier to just say, I can show you this is a finite number. I don't know what this finite number is, but I can show you what this finite number, that it is finite. As opposed to, I will tell you exactly what that finite number is. So, I mean, it's hard, right? Because you're adding infinitely many things. So let me just say for now, the book starts off with the two that you actually know this part too. So there are two types of series where we know exactly what it converges to. And these two are called geometric series and telescoping series. Everyone follow so far? Good, okay. So let's go over geometric first. So we'll get to examples soon. Metric series. So for a not 0, it's given as this, yeah? The reason is, I mean, if a is 0, every term is 0. So you're just adding 0 infinitely many times, so it's a 0. So it's like sort of redundant. So we don't really include that. So if I plug in n equals 1, I get a plus ar plus ar squared, so on and so forth, right? All right, one more. Yeah. So let's figure out what geometric series is. Like, how would you identify it? Well, how do I go from here to here, everyone? how can I go from A to AR? Good. And then AR to AR squared. How do you go from AR to AR squared? I mean, there are many ways, but what's the most obvious way? Like, I mean, it's the same as the first to the second. So what do you need to do to like go from AR to AR squared? The first thing you see. Oh, okay. So I mean, it's just this, right? Hopefully you all see like we're just multiplying by R to go from one term to the next. So this is what geometric is. Like each term is obtained by multiplying previous by a ratio. Yeah. So there's a common ratio, right? Because if you divide AR with A, you get R. Divide AR squared with AR, you get R. So and then so the R here is for the word ratio, if you like. So yeah. And what we figure is that this is equal to A over 1 minus R if absolute value of R is less than 1. So this is what I mean by we know exactly what it converges to, or it diverges if absolute value of R is bigger than or equal to 1. So let me just say it. I'm just gonna say how do I say this? It might seem weird to you, right? You're adding infinitely many things and you're getting a finite number, but it's entirely possible. So I mean, just to convince you it is, let's just consider when A is 1. If A is 1, then this is just 1 plus R squared plus R cubed plus R to the 4th, right? And the formula tells us this is actually just A, which is 1 over 1 minus R, right? I mean, provided, let's say absolute value of R is less than 1. So from here, right, we could check it. In fact, I'll convince you that this is indeed true. Like these two are actually equal. So one way to check it is if I multiply 1 minus R to 1 over 1 minus R, I should get 1, right? So if these two are the same, if I multiply this thing by 1 minus R, I should get 1. And sure enough, if you think about it, you do. Because if I FOIL the 1 to every term, you see I get this, right? Right? It's just an infinite thing. And now if I FOIL negative R, you see I get minus every term but the 1. Do you all see that? Right? So everything here will cancel. And then you're sort of left with the 1. Yeah. Everyone clear on this? Hopefully, I mean, it's not an actual proof. I'm just trying to convince you this formula is true. So so from here, right, we can I can also convince you why this is true. So again, if you take A to be 1, just for simplicity, let's just take R to be 2. Certainly absolute value of 2 is bigger than 1, right? If you write out what these terms are, it's this. So each term, 2 to the n, these things are growing, right? That's the idea. When you're bigger than 1, when you take powers, it grows. Like 2 squared is 4, 2 cubed is 8. It's just going to keep growing to infinity. So forget the sum part. Yeah, forget the adding part. Each term themselves are going to infinity. So if the terms themselves are going to infinity, already, then if you add them, it's still going to go up to infinity, right? Like it's not going to change. Like if your terms themselves are getting bigger and bigger, then obviously when you add them all together, they're going to get way bigger and bigger. So you can see it diverges. Is everyone clear with this? Before we're going to do examples now. But is everyone clear on like the idea of geometric series? Everyone good? Okay. So let's do examples now. So these are probably like your web assign or like written homework, I guess. So the actual problems are very simple. So all you need to know is this, the formula I just gave you, and then you can pretty much solve every question. This is it, right? So you just, I'm saying the goal is to just make it of this form. Yeah. So let's check it. Right now we're starting at 1. We're starting at 1. That's good. I need everything to the n minus 1 power. So how do I make 11 to the n minus 1 power? I mean, obviously these are not equal, right? So what do I need to multiply by to make it equal? So this is something you should know how to do. It's like rules of exponents, I guess. Mm-hmm. Good. If that confuses you, it's sort of like this. I have 1 over 2 cubed. How can I write it as something times 2 squared? Okay, because this is 1 less, right? N and n minus 1 is 1 less. So how can I write it? Well, I need to multiply by 2, right? To make it the same. So same idea here. And I'm gonna really do baby steps, just so we're all clear for now. 1 is just 1 to any power. So I can make this n minus 1. And we are done because we get this n minus 1. This is your A, this is your R. Yeah. We have wrote our series into this form. And absolute value of 1 over 11 is certainly less than 1. So we use the formula. This is equal to A, which is 5 over 11 over 1 minus R, which is 1 minus 1 over 11. And you get, what is that, 5/10? So this is a half. Everyone good on this? Let's do one more for practice. Example. What's the n? So let me just remind you, this is the formula again, right? So here they start at 1, so that's good. Now, I need something to the n minus 1 power. So this thing is already to the n minus 1 power. I don't need to do anything to it. I just need to change this, right? And you see, if you change this, it's the same idea, right? It's just 4 times 4 to the n minus 1, right? One-fourth times. And then we are golden because this is my A, the 1/4, and then my R is negative 3/4. Yeah. And certainly absolute value of negative 3/4, which is 3/4, is less than 1, right? So we could use the formula. It's A over 1 minus R, so 1/4 over 1 minus negative 3/4. So it's 1/4 over 7/4. So what? 1 over 7? Is everyone clear on this? Yeah, nothing too hard. So I guess the next question is, what if they change the index? What if we don't start at 1? How can we use this formula? And what to do that, you need to understand how to relabel the index. So let me just start off with, let's start with n equals 0. 2 to the n. So this, if I just plug it in, is what? If I plug in 0, I get what? 1 plus a half plus a fourth. It's this thing, right? Now, question, what if I wanted to change this to n equals 1 to infinity? What would I need to do? So will it be this again? Let me ask you, is this equal to the top? Let's check, right? If I plug in n equals 1, I get a half. If I plug in n equals 2, I get a fourth. And you see this series is just this, right? I'm missing this one term. Do you all see that? So obviously this is not right, but the idea is if you added 1 here, right, you have to subtract 1 to account for that, right? So what you do is you replace n with n minus 1. Now it's good. Now you're golden. Because if I plug in 1, I get 1 over 2 to the 1 minus 1, which is indeed 2 to the 0. So this is 1. Plus, if I plug in n equals 2, I indeed get a half. N equals 3, n equals 4. And you see that these two are just equal, right? These two series now. Does everyone see that? So you can always change the index, provided you adjusted the inside part. So I didn't go over this with the previous class, but let's just go over something the same, right? The same idea. N equals 3 to infinity, or let's just do n equals 4 to infinity, 1 over 2 to the n, right? If I wanted to change this to n equals 1 to infinity, what did I do to go from 4 to 1? I mean, how would you go from the number 4 to the number 1? What is at least what is one way? The most obvious way. Subtract 3, right? So I need to make up for that. So I need to, in a way, replace n with n plus 3 to account for that. Yeah? And you could do check, right? If I plug in 4 here, I get 1 over 2 to the 4. So this is the series. This is my series, right? The dot, right? This thing's the same thing, because when I plug in n equals 1, I get 1 over 2 to the 1 plus 3, which is 1 over 2 to the 4th. And these are the same series. Is everyone clear on this? I mean, you can always plug in terms to check, right? If you ever get confused. But this is really important. So does everyone understand how to like change the index of your summation? You will need to know how to do this for WebAssign, I think. So at least from, I guess, the past WebAssign I had when I TA math 2A, 2B, they had this. Okay, let's go to an example now. So again, let me just rewrite the formula for you, for since it's your first time seeing it. But it's still just this. Everything is this formula. So let's start at 0. I need this to start at 1, right? To use my formula. That's all geometric series is. You need to use the formula. So let's make it start at 1. But when I do that, what am I doing to go from 0 to 1? What operation do you do to go from 0 to 1? Right, it's the most obvious operation. You add 1, right? So how do you make up for that, for the inside? If I added 1 to the index, I need to do what? I need to sort of replace n with n minus 1, right? So your guess would be like this. And sure enough, you could check it, right? I mean, just check the first term. The first term here is 3 over 1. Yeah. Negative 2 to the 0 is 1. First term here is 3 over 1. Yeah. These are indeed the same. So, and then from here, it's the same thing as the last problem, right? I have something to the n minus 1 power. That's good. This is not to the n minus 1 power. Let's make it to the n minus 1 power by doing this. And hopefully you see by now that this is 3 times negative 3/2 to the n minus 1. This is your R, this is your A. Now, absolute value of negative 3/2 is 3/2, and that's bigger than 1, right? So here it diverges. Everyone clear on this? Okay. So knowing that, let's do one more. So this is like the last case you'll probably encounter, like the last different case. Is if you have something like this. Let's keep it at 1. I will write the formula for you again. Let's do this. This is E, by the way. So I'm starting at 1. That's good. I have an n minus 1 here. That's good. I just need to make this to the n minus 1 power. How would you do that? So does everyone agree if this was just some like 5 to the n, if it was something to the n power, we all know what to do, right? You just do this. I'll ignore the bounds just to make it fast, right? You know what to do if it's the n power, right? This would be 5 over 6 to the n minus 1. This is r, this is your a. Everyone agree with that? Like if you had a number to the n power, you know what to do, right? Is everyone clear on that? So ignore this question for now. Like if it was a number to the n power on top, you would know what to do. Does everyone agree with that? I need you to understand this part. So this is like kind of like the first two problems we did. Just changing that n to n minus 1. Does everyone follow? Okay. Then we are sort of done because e to the 2n is this. Do you agree? So we could just think of this instead of e to the 2n, we think of this as e squared to the n. Now we have a number to the n power. Yeah. And now we do the same. So think of e squared as like has the role of the 5. Yeah. So it's e squared times e squared to the n minus 1, right? And we are, done to have e squared over 6 to the n minus 1. So this is your a. Sorry, no, wrong one. So this is your a, this is your r. Yeah. And e squared is like e is 2.7 something. So when you square it, it's going to be bigger than 6. So this will diverge. Yeah. Everyone clear on this? Cool. Okay, let's go over telescoping series now. The best way for me to describe this is things cancel out. So the first type you'll see is if you're subtracting two fractions, or if it's something like this, if you're doing something where you have to use partial fractions, then chances are it's telescoping. So, I mean, let's just use partial fractions. Hopefully you all know what to do by now. Plus 2. So if I plug in n equals -1, I get a is 1. If I plug in n equals -2, I get b is -1. Yeah. So obviously this thing is just this. Yeah. Okay. So you could just write it out. Like you will see like things cancel. Yeah. So let's just see the first few terms. You'll see what's happening. That's why they call it telescoping. Plug in n equals 1. What do you get? Don't simplify. So I'm just asking you, like, when you plug in 1, what two terms do you get? So if I plug in n equals 1, I get this, right? Not plus, minus. Agree? Now this is for n equals 1. Now when I plug in n equals 2, what do I get? When I plug in n equals 3, what do I get? Do you all see what's happening? Sorry, 3. Ugh. Yeah, maybe I'll do one more just so you hopefully you all see what's happening. Yeah, basically everything but the first and last terms go away, right? Do you all see that? So this is what I mean by things cancel out. So, I mean, it could be, maybe some other questions. Not everything cancels, not every middle term, but most of it goes away eventually. So you would have to figure out, the pattern. But anyhow, but to do this formally, right? Obviously, your answer should be a half, right? Because this thing, I mean, the negative 1/6 will go away, and then you'll get like a 1/7, 1/8, 1/9. But like that thing is getting smaller and smaller, and this thing is just staying the same. So you're getting like a half plus something really, really smaller, getting smaller and smaller. So you should expect this to go to like 1/2, right? So like that is the answer. But like, just to do things formally, this thing is, remember the definition, right? And so let's write out, this is Sn, but let's write out what Sn is, right? This is when n is 1, I get a half minus a third plus a third minus a fourth. Same thing as before, right? But but I'm going up to n, right? So let's go up to n minus 1. So this is for n equals n minus 1. I get 1 over n minus 1 over n plus 1, right? And then plus 1 over n plus 1 minus 1 over n plus 2. Right? So I'm going up to n, right? And so this is Sn. And you see everything here cancels, but the first and last, right? So it's 1/2 and negative 1 over n plus 2. So this summation is just 1/2 minus 1 over n plus 2. And what happens when n goes to infinity? Where is this going to? Exactly. Yeah, so this thing's sort of telling you, like the terms here are going to get smaller and smaller. And they're going to keep getting canceling and becoming smaller and smaller. So this thing's going to go to a half. So this is like the actual proof, I mean like using the actual math definitions. This is just, to give you an intuition of what's happening, But I mean, from here you could easily see that this thing's going to be a half, right? So, okay. Yeah, so this is like formal proof, I guess. Formal way to write it, because we're using the actual definition. Okay. So let's just do one more and then we'll call it a day. So if you have to use partial fractions or something that looks like that, or if you see a natural log. If you see a natural log, there's a chance it's telescoping. Yeah. So, okay, how can I change my natural log? What rule can I use to take out that division? What is another way? Basically, I'm asking, what is another way to write? Yeah, subtract, right? And just to see what's going on, you could always write it, right? This, when I plug in n equals 1, I get this. This is for n equals 1. This is minus plus n equals 2 plus n equals 3, so on and so forth, right? And sure enough, what do you know? And so you see here, this is ln of 1 will always stay, which is 0. That doesn't do anything. And you see, you keep getting higher and higher things, right? You're gonna get like ln of a really big number, right? Or negative ln of a really big number, right? There's a negative here. So what is ln of a really big number? I mean, where's that going to? What's ln of infinity? Is what I want you to think of. So I have 0 minus infinity. That's like negative infinity. So this thing's gonna diverge, right? But let's do it, actually formally. So you should expect this to be like, to diverge. Again, we just use the definition. I mean, obviously on the final, you don't need to write the definition down, right? I mean, it's like multiple choice. So if you could see just from this, then like might as well save your time and just just pick the answer. So, but anyway, so this is limit n goes to infinity Sn, right? And let's write this out, right? This is ln of 1 minus ln of 2 plus ln of 2 minus ln of 3, all the way to, let's plug in n minus 1. And so this is for n equals n minus 1, and then we go all the way to n, right? So the next term's n. Right? And you see everything cancels except the first and last. So this thing is actually just ln of 1 minus ln of n plus 1. ln of 1 is 0. And again, like you said, when n goes to infinity, this thing goes to infinity. So this actually goes to negative infinity. So this thing diverges. Everyone clear on this and how telescoping works? Yes, no. So that's all telescoping is. You just need to write it out, figure out which terms will go away, like as you continue on, and which terms, and what happens to the terms that stay, right? Okay. That's all I have for today. So next time we'll go more into new tests that only tell you like whether it converges or diverges. It won't tell you like what the exact number is. And yeah. So there's still a lot more things to do for series. But I just want to go over these two things today. Okay, cool.